Welcome back, AP Stat. This is Chapter 24. We're talking about paired samples and blocks. So let's talk about what we do with paired data. This is a classification of data that we have not dealt with when constructing confidence intervals or testing hypotheses. All right, so we need to handle a paired data situation fundamentally differently than we have in hypothesis testing and forming confidence intervals up to this point. So, the health department of Lake County, Illinois, says our textbook, experimented with a 4-day work week. The mileage traveled by 11 field workers in a normal 5-day work week was compared with that of a 4-day work week. So we want to see if taking away a day of work either decreases or perhaps increases the productivity of these drivers. This is an example of paired data in which two sets of the same size are not independent. Two sets of the same size that are not independent are called paired data. All right. And we need to treat paired data different than two independent data sets. All right. These sets of 5-day mileage and 4-day mileage you see to the right are not independent. This sort of data most often occurs when we're investigating the difference between groups before and after treatment. All right. It could also relate to matched pairs. All right. So if we think that there is some kind of association between the folks in one group as opposed to another, maybe we take twins and we put one twin in one group and another twin in the other, or we put husbands in one group and wives in the other. Those would be matched pairs. That is also in the category of paired data. Because these kind of data are not independent, they are dependent, all right? We cannot assume independence here. That would be silly. We need a new technique to analyze them, and what statisticians have found to do in this case is brilliant, if you ask me. So we'll get back to the data about the truckers, but we're going to look at another set of data right here because this table really well explains how we handle this sort of situation. In speed skating, one skater lines up in the outer ring of the track and the other in the inner ring. And halfway through the race, the skaters need to switch lanes. Yes, this is very dangerous, but professional speed skaters are used to the danger. In fact, I would argue they embrace it. To the right are speed skaters' times in the outer and inner lanes. And that is starting in the outer lane and starting in the inner lane. They don't stay in the outer or the inner lane. That would just be straight up unfair. They do switch at some point, but it's starting in the outer lane and starting in the inner lane. And we want to see if there's a difference between those times. So to the far right are the differences in the times between the outer and inner lanes. And when comparing paired data, we perform a one-sample t-test. It's sometimes called a paired t-test or a matched pairs t-test. Our data are the column of differences between the two groups. So watch how this happens. We know that the skating pair number 1 here, the person who starts in the inside track and the person who starts on the outside track are related. It's the same heat. It's the same skating pair, all right? It's the same trial, okay? So these skaters are not independent, all right? But what is independent is the set of inner minus outer times, all right? So each one of these times is a difference of an inner time and an outer time, all right? So the one skater starts in the inner track, the second skater starts in the outer track, and then there's a difference. You'll notice that the inner and outer times are not independent, all right? One skater's skating may influence the speed of another skater, as it often goes in races. So we cannot assume that these are independent, but each difference is independent of each other difference because they are different races, different pairs. We can assume independence of differences between the inner and the outer time. So this inner minus outer is independent of this, which is independent of this, which is independent of this, which is independent of this. And since we have independence, that is the key that unlocks the door to hypothesis tests and unlocks the door to confidence intervals for paired data. That is how we get around the dependent sets. We take the two dependent sets, find a difference, which consists then of values that are independent of each other, and thus we can do inference. Brilliant, right? All right. We do need to check off some conditions and assumptions for a paired t-test. And first and foremost, we need to ensure that our data are in fact paired. The data need to be paired. That means we have two sets of equal size that are clearly not independent. If the sets are independent, you would use the technique from chapter 23. So the techniques we learned in this chapter will not work for sets of independent data. Look back at chapter 23 for techniques on how to do that. We need to assume independence of the differences. All right, so each difference, before minus after, one group versus another group in which the groups are dependent. You compute differences, but we need to make sure those differences from the paired data are independent, all right? So we do need to, if I'm going to go back to the last slide here, we do need to make sure that these times are in fact independent. And unless there's a clear reason that they would be dependent, in which case there's not here, in this case there's not, we can generally assume independence of differences, all right? Unless we have a clear reason not to, we can check off that box. All right, so back to this. We can check that with randomization. All right, so data are sampled at random or randomized with sound experimental methods. All right, if we're doing an experiment, randomization is done there, and 10% condition. All right, so unless we clearly break one of those two, randomization or 10%, we can assume independence. And that is absolutely the case with our speed skater data. All right. And the nearly normal condition, the set of differences, not the two sets, all right? The differences. It does not matter the distribution of the two sets. Specifically here, it's the differences must be approximately normally distributed, all right? It does not matter how the two samples themselves are distributed. The differences need to be unimodal and symmetric, which is nice because we're not always going to get samples that are unimodal and symmetric, but the differences of the samples, that's what needs to be unimodal and symmetric. All right, so we are back to the data involving the truck drivers. All right, so field workers for health department compare the driving mileage on 5-day work schedule with the mileage on a 4-day work schedule to see if the new schedule changed the amount of driving they did. We'll look at paired differences in mileages before and after. All right, so before the change, you have the 5-day mileage, and that will go to the 4-day mileage after. All right, and then we find a difference over here. So is it okay to use these data to test whether the new schedule changed the amount of driving? All right, so let's go through these conditions. Paired data, clearly these data are paired. There is a clear before and after. Moving on. Can we assume independence of those differences? The driving behavior of any individual worker is independent of the others. We have no reason that Jeff's driving would influence Betty's or Roger's or Tom's or Amy's or anyone else's driving. So the differences are mutually independent. That means they're all independent of each other, right? Since this is an experiment, we do not need to worry about 10% condition. We can just move on there. But just to make absolutely sure we can check off the box for independence, we do need to talk about randomization. All right. The mileages are the sums of many individual trips, each of which experienced random events that arose while driving. Okay, so just by the nature of the job, we can assume randomization. All right, so just by the nature of what we're doing here, we assume randomization. Nearly normal condition. This is one of the rare cases in which our histogram of data are begging to be analyzed. All right. Yes, our x-axis, the intervals, may be made to really drive the point home that these data are unimodal and symmetric. Nonetheless, these data are begging to be analyzed. All right. That is about as good of a unimodal and symmetric distribution as you could possibly want. Let's get to the analysis. We have checked off the boxes. All right, so here's just some information about how we would conduct a paired t-test. So once we've met the conditions, we're ready to test whether the mean of paired differences is significantly different from 0. We will test the hypothesis, the mean difference. So not the means of the two data sets, but the mean of the differences, all right? The mean of the before minus after. Is equal to delta 0. What's that? Well, delta is a symbol for change in mathematics, so change between before and after. But in the null hypothesis, you can assume delta sub 0 is 0. So you might as well just put a 0 right there. The mean difference equals 0. All right. We use this test statistic right here. We compare the average difference. All right. So the average of the difference is the sample mean difference. So if D bar right here is the mean of the differences in our sample, minus delta 0, so that's just 0, divided by the standard error for the random variable, the mean difference. All right. D bar is the mean of the pairwise differences, and is the number of pairs. La-di-da, we have the standard error, bada bing, bada boom. As you can imagine, this process is done on your calculator for you. Yeah, it's not terribly difficult here. One note I will make, we can model the sampling distribution with students' t model. So we'll be using the t model, the t distribution, n-1 degrees of freedom. And what is n? N is the number of pairs, not the number of individuals in our study. It's the number of pairs, all right? So sometimes the number of pairs is the same as the number of individuals in our study. Sometimes sometimes n we'll need to pay close attention and make sure we're saying, okay, it's the number of pairs, all right, not the number of individuals involved in our study necessarily, all right? And that's how we get our p value. All right. Here we go. Let's look at how we would conduct a paired t-test for the figure skater data from a couple of slides ago. So was there a major difference in speeds between the inner and outer speed skating lanes in the 2014 Winter Olympics? All right, so let's test this. Here are the hypotheses. The null hypothesis is mu sub d equals 0. That is, neither lane had an advantage. You do not need to write that neither lane had an advantage. You can just say the mean of the differences equals 0. That will suffice. The alternative hypothesis is that the mean difference is different from 0. All right, so the differences are on average not 0. All right. There is some difference between the before and after, or in this case, the inner time versus the outer time of the pairs of skaters. All right. So there you go. You have mean difference is not 0. This is the only thing you really need to have. Okay. So let's make sure that our assumptions and conditions are checked off. Paired data condition, the data are paired because racers compete in pairs. One influences another. That is just how racing goes. So you cannot assume independence. We are doing the right process. Moving on. We do not need to check 10% condition. This is, I guess, a small enough sample size that doesn't really matter. However, if you really wanted to, you could say we're sampling less than 10% of all speed skating races ever. That is certainly a guarantee there. You should be able to assume independence. Each race is independent of the others. That is a reasonable assumption. But just to make sure, randomization condition, skaters are assigned to lanes at random. Okay, so the randomization is met, and we can assume that each of the pairs of data, there's randomization there, so that is good. All right, the differences should be randomized. nearly normal condition. The histogram of differences is unimodal and symmetric. Yeah, we have a little bit of a blip right here, but it's not much. This is about as good as we can hope to have. The conditions are met. I'll use students' team model with 19 degrees of freedom. There are 20 pairs of racers. There are 40 total racers, but that doesn't matter. There are 20 pairs of racers. So we would have n minus 1 equals 19 degrees of freedom. All right. And that just tells us what T model we need. The calculator knows that honestly better than any of us. And we're going to perform a paired T test. All right. So let's get to the T test. So here we are at the calculator. I've entered the differences, that is inner minus outer, racer who starts in the inner track versus racer who starts on the outer track. I've entered those times. You only need to enter one list because we're already given the inner minus outer times. Now, there are instances in which you're not given the differences explicitly. You need to compute them yourself. Once we get to an example like that, I'm going to show you how to efficiently do that in the calculator. But for now, we're given the differences here. So now we're going to go to stat. All right, we're going to go to stat. We're going to go to tests, and we're going to do a one sample T test. All right, for a difference of means. Okay, so we are given raw data, and the mu sub 0 is going to be 0. All right, remember our hypotheses. The value in our hypotheses is 0. We go to list, that's list number 1, frequency, and everything checks off right there. So we go to calculate, and we have a p-value of 0.385. That is a high p-value. That null hypothesis is safe. So we entered our differences into edit, used a one sample t-test, and got a high p-value. P-value is large. Events that can happen more than a third of the time, 0.385 is more than a third of the time by chance alone, are not remarkable. So even though there is an observed difference between the lanes, we can't conclude it's due to anything more than just random chance. This is a very replicable result. All right, we could absolutely see a difference of about 0, about a third of the time. All right, so there's not enough evidence to reject that null hypothesis. Okay, there is insufficient evidence, says our textbook, to declare any lack of fairness due to which lane the skater starts on. All right, so there is our conclusion. So now we're back at the truck driver data and the analysis of it. We want to test whether a change from a 5-day work week to a 4-day work week could change the amount driven by field workers of a health department. And we've already confirmed the assumptions and conditions for a paired t-test are met. So here's the question. Is there evidence that a 4-day work week would change in some way, shape, or form, whether better or worse, how many miles workers drive? All right, so the null hypothesis is there is no difference between the 5-day and 4-day mileage on average. All right, and the alternative hypothesis is that there is some kind of difference on average. We've already checked assumptions and conditions. Then we're going to enter the differences into edit and use a one sample t-test again and state the conclusion in the context of the problem. And here I have intentionally chosen the table that does not have the differences so I can show you how to generate them on the calculator automatically. It is very easy, and I think you'll like it. So I entered the data again into list 1, but also I entered data into list 2. In list 1, I have the 5-day mileage numbers, and on list 2, I have the corresponding 4-day mileage numbers, and I've paired each of the driver's data next to each other. All right, so this would be Lee's data. The next one up would be Leslie's data. The next up would be Larry M's data. And so I made sure that the data were paired just as they are in the table. That is important. All right, so what I'm now going to do is go over to list 3, and I'm going to hover over list 3. All right, and I am going to make this the before minus after. All right. The before minus after. And I'm going to say, let's hover over list 3 and then put in list 1 minus, and then second list 2. There we go. And now I'm going to hit enter. And it's automatically going to spit out a bunch of differences. All right. And those differences are what I'm going to work with for my t-test. So I've automatically generated the differences. Okay. So I'm going to go to stat. I'm going to go to tests, and I'm going to go to number 2, which is t-test. I again have raw data. Mu sub 0 is 0. All right. List is not list 1. It's going to be second list 3. Oops, that's wrong. I'm going to do, let's get out of alpha here. Do second list 3. Okay, there we go. Frequency is 1. There's my alternative hypothesis, and I'm going to hit calculate. All right, it's very important that you change that list to list 3 because that's your list of differences. And here is your p-value, 0.017. Okay, 0.017. And we're going to note the mean difference here. The mean difference is a positive number. So what's our conclusion? The p-value is small, so we reject the null hypothesis. There is significant evidence that there's a difference between the mileage driven in 5-day versus 4-day work weeks. Since the mean difference for our sample is positive, we can conclude that the 5-day work week is associated, and this is a causal relationship because this is an experiment. This is a well-constructed experiment. So we can say there is a causal relationship, all right, with increased mileage, all right? And we can say that because we computed before minus after 5-day mileage minus 4-day mileage. So since our mean difference is a positive number, that 900 odd value that we got from the calculator, we can say that increasing the number of days in the week has a causal relationship with the amount of mileage driven. The more days you work in the week, at least between 4 and 5 days a week, working that 5-day work week does increase your mileage. Much as these truck drivers might not want to admit the 5-day work week is better in terms of mileage, we have shown that it is, at least in this case.